The idea is that to take this highly successful comb concept, which has been applied for years now in the infrared and the visible, and now apply it to the extreme ultraviolet. And basically the main application is precision frequency spectroscopy, where you're trying to look for a specific transition in the extreme ultraviolet and then measure its energy very precisely, especially transitions that are already naturally very narrow, because the comb teeth in that frequency comb, each energy spike can be extremely narrow, and so you can use just one comb tooth to scan across a transition and measure its energy position and width very precisely.
It was a major setback for spectroscopy, that the power was very low. You need enough power to be able to observe the results of spectroscopy precisely. In order to gain from the precision of your color, your frequency being very well defined, you have to have enough power. Otherwise, noise and background effects will just drown your signal. You need your signal to really hold its head up above all the noise. And that has actually been holding back precision spectroscopy in the extreme ultraviolet. This issue of the power has been holding back progress on that front. And now we finally have pushed through this barrier.